Hi everyone, welcome to part 3 of this video series on discovering novel strategies to defeat COVID-19 through knowledge graphs. In part A of this video series, I gave you an introduction as to why we require knowledge graphs to fight COVID-19. In part B, I had a review of existing knowledge graphs and discussed the limitations in them. In part C, I'm now going to discuss how we can go about in designing a universal COVID-19 knowledge graph and what are the challenges that we face there. As discussed in part B, a universal COVID-19 knowledge graph should comprise relations between all possible entities or processes from all possible COVID-19 research papers. What is very important is that the possible strategies to defeat COVID-19, which are discussed in different research papers, should be an important aspect, should be an important element in this COVID-19, in this universal COVID-19 knowledge graph. This is something which is missed out in all the COVID-19 knowledge graphs that I've seen so far, and I'm amused because this is one of the most important reasons why we need a knowledge graph at all. So whatever suggestions different authors have given regarding development of drugs, regarding development of vaccines, or regarding other vulnerabilities, regarding some vulnerabilities of the causative virus of COVID-19, which may help us exploit them. The different entities which are related to all those processes, all those things need to be linked together so that it's faster for us to come to solutions to COVID-19. An ideal universal COVID-19 knowledge graph should be one, which should be easy to visualize and should be interactive. When it was discussing the COVID-19 knowledge graphs in the previous video, I pointed out that, for example, the IBM COVID-19 knowledge graph is very helpful when it comes to finding which entities are present in which research papers. However, if one were interested in building the relationships between different entities, that wasn't very intuitive, it wasn't helpful, it didn't have a UI for that. One had to go to the respective research paper and see the information for oneself. Similarly, the Amazon COVID-19 knowledge graph is very helpful when it comes to repurposing drugs for certain diseases. But I'm not sure whether it has a UI. I didn't see a UI corresponding to that. And even if there were one, it would suffer from the fact that it is just limiting itself to drugs, genes, diseases, etc. It is not the entire COVID-19 knowledge graph, Amazon COVID-19 knowledge graph is not focusing on other factors which I discussed in my previous video. It is not focusing on, for example, the environmental factors. It is not focusing on the results of different experiments. And there are other points which I discussed in my previous video. Then you had the biomedical knowledge miner, which was slightly more intuitive compared to IBM and Amazon COVID graphs when it came to visualization. But because it required inputs in the form of Bell, and also because it had less data, so it was useful only up to a point. So people like me, for example, do not find Bell at all intuitive. However, there was the knowledge graph known as COVID Graph Explorer, which was quite easy to visualize. It was quite intuitive and interactive. And I'm going to revisit it. The reason I'm revisiting it is because I'm taking it as a kind of a model for building my own website, which will be powered by this universal COVID-19 knowledge graph. So this is the COVID Graph Explorer that will load now. I consider it as one of the best forms of visualization which I've seen so far as COVID graphs are concerned. Suppose I were interested in finding a research paper related to SARS. I would just enter SARS, it would show me all the papers. So it is showing me 10 papers on one page. All right. Suppose I want to select one of these papers. Suppose I want to select this paper. And I want to load different details related to it. So, for example, the information which I may be interested in could be what are the genes which are contained in this, which are being referred to in this research paper. So when I click on it, it shows me the list of genes that are there. And if I want to load all the genes, I just click on load all, and then very soon it is loading the genes which are referred to in that paper. Suppose I want to get further information on the SARS gene, I can choose any of these options and click on it. So this will show me all the related tissues related to that gene, and I can see all of them. So I believe tissues which have that gene in them, and then I can load all of them, or I can choose one and load that specific tissue. And though it takes some time, but it loads all the tissues, it loads all the tissues, and then you can go to each and every tissue and see the respective information. For example, I can go to this tissue and see the expressing genes which are present in this tissue. So it could be other genes besides my gene which I chose. So all the genes which are present in this tissue. So this is a very helpful form of visualization whereby I find it intuitive to navigate through the graph. So this is a standard as of now that I am taking for building my own website related to knowledge graphs, related to universal COVID-19 knowledge graph. That is about visualization. Now, when it comes to creating a knowledge graph, what are the basic elements we require? Of course, we require relationships between different nodes. We require nodes and vertices. Those nodes will be the source and target nodes. And you have vertices which will represent the relationships between those source nodes and target nodes. From the research papers, it is mandatory to extract the source and target relations from all the relevant sentences or groups of sentences. Once this information is extracted, a knowledge graph can be plotted, and then based on the knowledge graph, on top of the knowledge graph, we can write several functions so as to just limit ourselves to seeing information related, say, to a particular node, or all the nodes connected to a particular node up to a certain depth, and so on and so forth. This is something which I will discuss more in my next video when I actually will show you my own knowledge graph that I've created. But suffices to say, we require the triplets for source, relation, and targets to be extracted from the research papers. We require plotting of the knowledge graph, and then we require more functions on top of knowledge graph, on top of that knowledge graph, so as to uh, check for specific entities that we are interested in. What I present here is an example of a research paper from which I started creating knowledge graph by using the current Python NLP modules that we have. So the paper which I considered was Shielding and Beyond, the Rules of Glycans in SARS-CoV-2 spike protein. And if I go to this paper, as you'll see, I have this paper loaded with me. So this is a paper, this is a pretty extensive paper, and I would say it's biologically dense. What I did initially was, rather than doing the process of extracting automated extraction of subject, source, target, and relationships from this research paper, I just took two sentences to see how the existing algorithms work. I took some 20-30 sentences, and I extracted those sentences, loaded them in my, I stored them in my GitHub, and this is the file which you have, this one. And if you see these sentences, these are not very trivial sentences. It's nothing like John hit Mary, or say Tom plays with Trevor. It's nothing like that. You have sentences which are complex, which have many clauses in them. And then when I actually run my spacey algorithms, spacey functions to extract information, to extract the source, target, and relations, I find the results are not very encouraging. Moreover, I have tried different code which is available online for extracting these relationships. And every time I find when I extract these relationships, the results are not up to the mark. They are far away from the mark. Let me give an example. Here I'm loading an example of a code which I used for extracting relationships. And I'll show you when I use this code for extracting relationships on those some 20 to 30 sentences, what kind of results I'm getting and how far are they from the accurate results. So it's connecting, this is the Google Colab interface, that code was executed in Google Colab. So most of the code which I used for it was taken from the internet. I try to use the best functions available, but then despite the variety out there, the results were not so encouraging. So herein I'm using spacey functions. I'm just importing the relevant modules and I'm loading my zip repository, which has this file, the file related to sentences from the paper on spike protein glycans. All right, so I think this was already loaded by me. I had opened it previously and I'm checking the sentences that are out there. I'm extracting the roots from those sentences through this function, extracting the entities through this function. So these are functions when actual parameters are passed will be used to extract the root words and the entities. So it's basically the same thing. I'm just trying to re-execute less in case there is some other result which shows up here. If the file was updated. No, it's the same. So when I extract my triplets, what I see is source, target, and edge. And what you see is you have, if you compare with the sentences which you had earlier, this is what I get as the triplet. And you might not even look into the sentences you have there, and you would intuitively feel that this was exactly, this was not something which we were looking at, which we were trying to look at. So it's not that coronaviruses are SARS-CoV-2. This still makes sense, but derived set provide viral RNA, which is initial host cell, where we divide it into subunits, likely TMPR, this is site, believed infection, and so on and so forth. So what I mean to say that the results which we are getting from automated extraction are not so useful. And when we actually plot these relationships, this is just a plot of these relationships. I'll do it again just to provide the updated set, if any. And you see, when these very things, source and target, are linked just in the form of a graph, you don't find it useful again, because if you have a relationship such as AC to host and interaction, what does it convey to you? It doesn't convey to you anything useful. Now, why are these? Why is this code behaving this way? As I mentioned, the code, the sentences over which this code is running, are not simple sentences. They are complex sentences, compound sentences, sentences which have multiple clauses in them. And rather than having just a single noun as a subject or an object, these sentences have multiple clauses where you can have multiple, what I may call, subjects and sub-subjects and sub-objects within each clause. And it will be important for us to extract them individually. For example, a sentence like the S1 subunit contains an N-terminal domain entity and the receptor binding domain RBD, where the receptor binding motif is responsible for the interaction with the angiotensin converting enzyme ACE2 receptor to gain entry into the host. Now, this is one sentence, but then it talks about the relationship between S1 subunit and entity RBD and RBM, and then it talks about what RBM is doing. Further, you have even within RBM, this is talking about the process which is going on, and this also talks about the objective of the process. So these are things which you would rather like to be present in different, as different subject object relationship triplets, rather than just one subject object relationship triplet, because this is what helps you build a knowledge graph more extensively. You have more nodes in the graph which can be connected with other nodes. However, this is not something which the current algorithms allow us to do. So there is a great level of what I call inaccuracy as far as extracting the information as per our requirement is concerned. So this was something, there were plenty of algorithms available. So if you Google how to extract, how to do knowledge extraction, how to do extraction of knowledge graphs from text using Python, you would find plenty of links. I tried a large number of those links, but couldn't find very useful results. And in case you are aware in case you are aware of any foolproof or close to foolproof algorithm which may help me extract these identities, and not only the identities are easier to extract. More important is to extract the relationship between these entities. Then do let me know. So entities can be extracted using the NER module, or what you have. So the NER is the named entity recognition module, or simply the entity recognition module. So that's very helpful. But then uh, what is of concern here is not just the entity recognition, is not just the entity extraction, but also the relationship between different entities. Another challenge, a serious challenge which I found related to extracting data for these knowledge graphs, is that there is a significant amount of data which is present in tables, graphs, and figures, and you it's difficult to extract this data. So if you were to extract data from figures, you would need some other tool. I mean, you just can't feed it into a Python program just like that. You would need, if you it's different from a text file. You can't put it into a text file and feed it. You would have to have some other modules for that. You would have to have some other tools for that, and even those tools may have their own limitations. So, if for example I was interested in the fluorescence site between S1 and S2 uh, with respect to the spike protein, and suppose I was interested in knowing where that fluorescence site lies. So I would have to extract this information from this paper. Similarly, you had issues with tables. Some of those tables in these documents are quite straightforward. So if the documents are present in an HTML format, one could, for example, extract the table tags and make use of the TI and TD tags to extract the relevant columns. However, as I demonstrate, there are plenty of tables where you have information stored in a non-structured format. For example, bills, which is talking about a list of registered clinical trials concerning BCG vaccine and COVID-19. So this was one thing which I discussed is the relationship between BCG and COVID-19 vaccine. This was something which I discussed as one of the limitations. So an example of a category of limitations of of many of the knowledge graphs which we have. Now I'm just showing one of the tables which occurs in this paper. And if you look at this table not only has names of continents and countries, but it is also talking about the percentage of high mortality risk age group. It is also talking about a climatic zone and in terms of latitudes and so on. So these are actually different categories, and you can't really simply extract them out. So as human beings, we know that these are different categories, but it will be difficult for a program, for an automated script, to be able to extract them. So I would say that this table is wrongly structured. It should have been in the right format, but it is what it is. Similarly, you have the other important thing that I was talking about, the possible strategies against COVID-19 which may be exploited to develop solutions, to develop universal treatment against COVID-19. Now, it is not as if the authors present these possible strategies in a very specific format. It's not as if they reserve a space, a line for this. There are different terminologies which we use to describe this. Some may directly say that this may help in vaccine development or this may help in drug development. However, some others may simply say it is useful for preventing infection, this is useful for dealing with infection. There may be other clauses, there may be different forms in which this knowledge will be present, in which this information will be present. And it will be difficult to extract all the possible forms from by using an automated script. So of course, we can search for some specific words like strategy, like vaccine development, like drug development, etc. But there's a great chance that we'll be missing out some other pieces of information which are related to this, but which may not be extracted by automated script. And what this all points to, given the complexity of extracting the information from these research papers, given the inaccuracies that show up, given the dense language of many of these research papers, given the different kinds of formats, the tables, the charts which are present in them, given the fact that the kind of information which we require may not be present explicitly and we may have to infer it from the document. What it what I am tempted to feel that if I spend a lot of time in trying to automate the process and trying to remove the inaccuracies, it will really take me a long amount of time, and even then, I will not be very sure whether those inaccuracies are resolved. However, it will be way faster and it will be much more easier if we were to do this exercise manually. The challenge there is there are plenty of research papers. There are more than 50, 60,000 of research papers. One person cannot read them all. One person cannot extract the relationships. But if this task were to be distributed amongst us all, we should be able to do it. One person were to take up one research paper, or even half a research paper, one fifth of a research paper, they should be able to extract the information in the required format. And what we would then be able to do would be to build a golden data set, a golden curated data set, which would have the source relationship and target relationship triplets, which can then be used to build a universal COVID-19 knowledge graph. And it is this thing that I plan to discuss extensively as part of my next video. Thank you very much.